So thank you for having me here. It's a really honor to follow these speakers and to be here actively with my presentation because it will be kind of different perspective. It will be about the hydrogen entry mostly and the identification of some critical parameters for hydrogen entry in the natural gas system. So I'm the PhD student in Tomáš Prošek's group in Prague, and we are currently working with two more research institutes and with industry partners to develop some practical tool to assess the hydrogen readiness of their system. So that's the part of the project, these results. I think I don't have to talk much about the hydrogen injection motivation to the natural gas system and the necessity of the experimental research here, but I just want to express here that we are focusing mostly on underground gas storages, which provides us the most complex part of the natural gas system. All of three hydrogen embrittlement factors here are really variable. Here we can meet a lot of steel grades in different states because we in Czech Republic have 9 underground gas storages, mostly depleted fields, and they are in service up to 60 years. So you can imagine then they will be in kind of different state with different surface state also, and they are mechanically loading with different regimes from pressure fluctuation, but also from vibration from compressors and so on. And also about environment, it's most variable here compared to, for example, transport part of the system. You can have dry gas, but mostly with some humidity, and also there is a lot of contaminants in this part of the system. And compared to the transport part, also higher pressures and temperatures, which are changing in the service life. And of course, in the future, there will be gaseous hydrogen, and that's why we are doing the research here. So just briefly about the contaminants, there is a lot of humidity in the natural gas because these facilities are here not just for the storage of hydrogen or today's natural gas, but also for its cleaning before it's transferred to the customer. So there is a lot of formation water, which is underground water driven with natural gas from the reservoir during the Václav season, and also some organics like hydrocarbons, because these depleted fields was original for also oil, not just for the gas, and some medias for the processing the natural gas, usually glycols for drying and so on. So the hydrogen entry in nowadays scenario is strictly corrosion-induced hydrogen, where the mechanism is cathodic reduction from corrosion itself or cathodic protection of the pipelines. In the future, that's the most reliable situation for the transport part of the system, just dry and natural gas. It will be blend or pure hydrogen, whatever we will see. We know that this multi-step mechanism is quite different. There was a really nice speech from the Professor Cheng in details about this mechanism, that it has to happen on specific sites, but it can happen under the service condition. And for the underground gas storages, it will be the combination of these two sources, and very little is known about it. So that's where our focus is. We are modeling these situations with corrosion exposures and with autoclave. Then we are quantifying hydrogen with TDA and trying to identify critical parameters for hydrogen entry. And of course, then we are trying to connect it with the mechanical testing, but we also have, as many researchers, just the electrochemical in situ testing. So we are trying do our best to really reach some relevant concentration and some trustable data for this practical tool. So first of all, it was the mapping step to really understand what is happening there, what are the source of hydrogen in the underground gas storages. So we received a lot of samples of the contaminant of 3 different types: formation water, vapor condensate, mostly hydrocarbons, and these glycols for drying. We did some characterization, but the most important here was the characterization of hydrogen uptake in this part. And of course, only the formation water was recognized as some source of measurable amount of hydrogen in the steel, and it was connected with corrosion rate. We did a massless test here to evaluate the corrosion rate. So we approached to some sampling step of these formation waters directly from the different part of the reservoirs where the formation water is typically present. And it was quite surprising for us that it can differ really significantly, because at the beginning we worked just with the stored samples. There was some hydrogen uptake, but not so dramatic. But when we did some testing with the fresh samples, there was quite high differences between these samples. And we did a lot of characterization of these samples. I don't want to overwhelm you with the results, but the only thing you should notice here that all the compounds or the values are quite low. These are results just for the recognized hydrogen recombination poisons, which can be the cause of higher hydrogen entry, but for now it's still ongoing research, but for now we are not able to pick only one or recombination poison which is responsible for it. So it is still some work in progress, but we know that this presence of formation water can be a problem, its nature can be a problem. It can also be connected with some microbial life. We had this suspicion from the beginning, because if you would be able to see it and smell this sample, it really goes to your mind that there can be some life. Even some results was, for example, a higher amount of ammoniums and iron. We had a suspicion that there could be microbiological induced corrosion, because this is a quite well-known issue in the gas industry. So we did just some simple tests with treatment of the formation water by boiling or addition of biocide that follows the mitigation process in gas industry. And we see that there is really significant difference in the results. So that is the evidence for now that MIC can be another critical parameter when you are evaluating the hydrogen entry in such conditions. But with MIC, you need multiple lines of evidence, and even though you are not able to say that MIC necessarily goes 100%, so that's kind of tricky, but we know about it, and we are still working on some methodology to sampling, characterizing, and then implementing it into our results. So now let's move to some purer source of hydrogen. We use in our labs just pure hydrogen, but we are following some mostly discussed mixture with the natural gas, 20% of hydrogen. So the total pressure of our pure hydrogen is somehow correlated with the partial pressure in this discussed mixture. And as you can see, we are not able to measure even after the 6 months exposure, after somehow higher hydrogen pressure to be really on conservative side, the hydrogen entry. I have to express here that these are just bare sheets, and really this mechanism isn't happening here much. But if we are combining the gaseous hydrogen with another sources, with corrosive environment, we can see that there is the significant increase in hydrogen entry, and it's mostly pronounced when the steel is in direct contact with the water and in the high pressurized hydrogen. We used here just some plain model of formation water with same level of chlorides as in the formation water is usual, and saw this result. So we was curious what are the factors that are driving this promoting effect. So we did some more testing with the focus on temperature. We saw that there is a negligible effect of temperature on this promoting effect, but it's clearly driven by the pressure of hydrogen. But still, we are working on it with the effort to understand the mechanism behind it. It works also with the demineralized water. We did some more sampling, but still we don't have we have some results for the formation water, and of course, because the absolute amount of hydrogen entered from the formation water is higher, even the synergy or the promoting effect can reach really high absolute values of hydrogen in the steel. So that's something. What are the critical parameters? Presence of formation water, its nature, and also possibility of MIC should be taken into the account. And then we are running some mechanical testing where we are trying to play with parameters of it to really receive some more relevant data, because we started also with the basic solution with the addition of the recombination poisoning, and we saw drastic effect of the hydrogen mainly on elongation, but we know that this is not a realistic scenario. So now we are using this milder approach to it, and still we are able to see some effect. But we know that it's a really big simplification compared to the gaseous charging. So let's hope that in the future we will be able to connect it with and compare it with some gaseous hydrogen charging. And we are also trying to quantify the hydrogen. We are measuring TDA after the fracture, and we are able to see that more served conditions of charging are the higher the amount of or area for the brittle fracture. So yeah, that's it. If I can conclude it quickly.
Please.
Critical parameters are presence of formation water, its nature, maybe possibility of microbiological induced corrosion, and we all know that it is important to set the parameters of the charging with hydrogen appropriately to really receive some trusted results. So thank you for the attention.